still about co-simulation, but this is actually about one specific case. And this case is basically a feeding system for mink. So I'm going to show the simulation now for the end result. And what it actually shows here is what it is actually intended. That you feed out at specific positions on the top level, and that you have a standard vehicle there added onto robotic capabilities so it's able to perform this action by itself. Seems pretty easy, right? So when we started out, I was having this understanding that we had this feeding system, this vehicle that we needed to automate, and we had this mink farm that we needed to feed all these animals in. Okay, that sounds pretty easy. Trust me, wasn't it? Because then we are getting back to some of the problems. So my understanding was, okay, we have a vehicle, we have somewhere we need to pick up the fodder for the animals, and we have somewhere we need to place it. Again, pretty simple. I had basically, because of my robotics background and my software background, I have no understanding of how systems like these work. So what you could do is actually split this up in a number of cases instead of solving it all at once. You need to have a robot that's able to move, pick up some fodder, and run all the balls and place it at the specific positions that you want it to. Okay. I've already done some simulation, so let's try to deploy this on a feeding system. And again, it basically, we takes out the small part that we tune in the parameters for this vehicle so they actually match in the simulation, and then deploy the controller onto the real system so it actually works. So it's kind of a reuse of an older model, so don't try to invent a new model, just reuse the old. So we added the control parameters and it worked kind of nicely. The other part was we needed to place the food or the fodder at the specific position, so we would kind of like to avoid to place it in between. So, based on what I perceived until now, don't remember the first simulation. I did this. I got this small farm and I started feeding out. This was kind of logical. This should be the way it should be done, right? And so, could we do this in another way? What about on both sides? That would be more efficient than human, right? You could, and if you space them apart, you can actually use the same pump to feed out. You just have to switch between them. Also, something you wouldn't do in real life is do this crazy combination of different feeding systems. When you do simulations, you kind of want to explore to see what could we actually do. So the advantage here is that you just place them apart, and one of them I've provided the possibility to both feed at the top and at the bottom. That's another system that you would kind of like to implement from the start. What about another process? What if we made the arm go up instead? Would that be another way to do it? It's so much easier when you can kind of present your idea to the project partners. This is the way I envision the system, how it should actually work. controller actually started to make mistakes. So if we take this one from the start again, you would actually see that it starts placing the food or the fodder at the wrong position. And that's not what I want to achieve. So right now I have just a simple simulation that do something. It shows nicely, but it's not actually performing what I want. It's quite clear from the simulation that it's feeding out at the wrong positions. It's actually also able to drive through all of the obstacles. So, evaluating on this a bit, I added a check for, is it actually placing the food at the correct positions? And are we actually trying to hit something right now? And then we started researching how fast could we actually go with the system. Just in this small farm. So here it starts feeding out at the top. And then it hits the obstacle and gets down and feeds at the bottom. So when I showed this to people who is knowledgeable about feeding in these areas, they would actually say at the first, you never have a system where you feed at the top and then feed at the bottom in the next place. So what I was seeing was kind of silly. And there was this mistake in my model, because there's no poles in the middle, so you won't have these obstacles. But based on my perceiving, I'm a software robotics engineer, I was sitting and developing a control for a system that was doing something that was not completely what the customer wanted. So the next solution was we moved on to this vehicle. And what you see here is there's no pole in the middle, and we're actually able to run a bit faster right now. It's actually even able to run faster than this, but you also need to be able to brake before you hit something. And you can slow down if you know where the obstacles are, but you could also encounter unknown obstacles. So we have like bumpers in front and the back, and also a laser scanner to detect stuff like that. But now we have actually defined this feeding system, and now we kind of have an idea how it should actually work on the real system. So let's try to deploy it. So we're again running with the same auto steering from before. It was one simple case that we solved. It's basically a separate system that's running by itself. It's just following a pre-planned route. And then we have the feeding system. That's also a separate case. You're just looking at one case. It needs to be able to feed and do this option. To run the controller and place the food at the correct points. So what I would have discovered, that some of the stuff that we learned is that if you have obstacle inside the hole, we would have to actually run slower. And if we had to switch, we would also have to run slower. But it was scenarios that would never happen in the real world, but when you sit as a software engineer, it's actually a possibility, so you don't perceive candidate solutions where the system could actually go wrong, or just you don't need to solve this. You're actually sitting and solving a problem that you don't need to solve. It was actually much more simple to solve. Also, the auto steering part is, you see, when you have an obstacle, like when it stands in front of the robot, it's basically also a limiting factor of how fast we can run, because there's a lot of people who would claim, okay, why can't you run faster? Well, there's always safety reasons. You could also get the arm to move faster, but that's also a safety factor. It becomes much more clear when you can do the simulation and see, okay, this is actually what we would gain if we was running 20% faster in the simulation in terms of trying to actually get the system to run that fast. So this is basically an example of how co-simulation using different tools can be used to do development of robotic systems. So I hope I was a bit explained this area so you were actually able to understand it. And is there any questions?